The most common empty orbitals are going to be A, sigma star, and pi star. Remember that the empty A orbital is simply an atomic orbital that's unfilled, and so you may see this represented as simply a 2p orbital. It's often a 2p orbital on a carbocation, but it can also be an empty hybrid. For instance, in the vinyl cation, there is an empty sp2 hybrid orbital, and this would be an example of an A. It's an atom-centered, localized orbital that is empty and does not contain electrons, and that's what distinguishes it from the N orbital. The A does not contain electrons. The sigma star is a second example of an empty orbital, and that essentially looks like this. Remember, we have a node between the nuclei in the sigma and the sigma star orbital, and represents a sigma antibonding orbital. And then finally, we have the pi star orbital, which looks kind of like this from a top-down view. It's two p orbitals that are out of phase with one another. So maybe something like that would be a pi star orbital. And again, the pi star orbital is relatively low in energy, so we see it react quite often as an electrophile. And we also often see the sigma star and A orbitals act as electrophiles as well. So all three of these can act as electrophiles. So one thing I think that's pretty cool at this point is that knowing those 6 orbitals, we now have 9 kinds of frontier orbital interactions we can think about. And we call these interactions frontier interactions because it's really the interactions between the highest energy filled orbitals and the lowest energy empty orbitals that are the most favorable. And I won't go into too much technical detail on this, but you should imagine that it makes sense on the basis of stability. Filled orbitals that are very unstable are going to be much more willing to donate electrons than orbitals that are lower in energy that contain electrons. Now, if the orbital does not contain electrons, then the lower in energy it is, the more willing it is to accept electrons. That's why empty orbitals that are reactive are low in energy. Filled orbitals that are reactive are high in energy. So what we typically, terms you will see are LUMO and HOMO, this idea of the lowest unoccupied molecular orbital, that's what LUMO stands for, and the highest occupied molecular orbital, or HOMO, and that's what HOMO stands for. Now what you're going to see is that the filled orbitals can act as HOMOs, the N, the pi, and the sigma star, and the empty orbitals can act as LUMOs, the A, the pi star, and the sigma star. And the reason they're given in this order is that this is an order that you should commit to memory. Sigma orbitals are the lowest in energy, pi orbitals are the second lowest, and then N orbitals are the third lowest, or the highest energy filled orbitals. Then moving on up, A orbitals are slightly higher than N, moving to pi star and sigma star. So really it's the A, the N, the pi, and the pi star that are going to be your most reactive orbitals. And remember, like I said, you can see these on Lewis structures as Lewis structural elements. So a double bond will always bring with it a pi and a pi star orbital. A lone pair will almost always, unless it's involved in resonance, occupy an N orbital. A sigma bond, of course, brings with it a sigma and a sigma star. So when you see those elements, that's how you should start to think about reactivity. You see a lone pair, zero in on its reactivity as a nucleophile. If you see a pi bond, think about its reactivity as a pi nucleophile. Now, what you're seeing on this table are the 9 possible frontier orbital interactions that we can think about. So taking the 3 filled orbitals and the 3 empty orbitals, there are 3 times 3, are 9 possible combinations of filled to empty interactions. And we'll look at examples of almost all of these kinds of interactions next time. But it's interesting to think about that all of organic chemistry, nearly, can be described by these 9 frontier orbital interactions. And in thinking about these, we'll develop a list of what are called elementary steps, which are curved arrows that are essentially found across multiple mechanistic contexts in organic chemistry. So a mechanism might invoke a series of these elementary steps, and by understanding each individual elementary step, you can really get a feel for the orbital basis of the mechanism and how you can think about the orbitals combining and some of the stereochemical, energetic, other consequences that that might have on the reaction. So keep this table in mind as we move forward. For every elementary step we identify, we'll come back to this table and think about the orbitals that are involved and how that influences the step, energy-wise or stereochemistry-wise, or thinking about some other consideration. Finally, I wanted to close with a few thoughts for next time. So as I said, all organic reaction mechanisms are based on simply sequences of orbital interactions, right? These HOMO to LUMO donation type interactions dominate organic chemistry and really control reactivity in a very profound way. Can we systemize organic reaction steps? Well, yes, absolutely we can, because those 9 frontier orbital interactions are really the only kinds of orbital interactions that we can think about and really represent how electrons move at the most fundamental, lowest level possible. So if you understand MO theory, then really you have a lot going for you in terms of understanding organic reaction mechanisms. So next time, we'll take a look at some elementary steps of organic chemical reactions. And if you're studying organic chemistry on your own right now, this is hopefully going to be a great tool for you because it's a very generalizable scheme. You can look at mechanistic steps in a variety of contexts and apply what we've learned and what you're going to learn about the basic molecular orbitals to the reaction steps you're looking at. And hopefully it will enhance your ability to learn, understand, and appreciate the mechanistic steps of organic chemistry.